Okay. I do have a doubt. Number of exchanges அதெல்லாம் பார்த்தோம்ல. Number of exchange and symmetry part எல்லாம் பார்த்துட்டோம். Okay. Yeah, we have done this. Half filled. Okay. So do you want me to do chromium and copper once again or we'll proceed? Yeah. Appo, sorry, some once revise. Okay. See. இப்போ வந்து chromium is 24. Okay, actually 1 to 30, that is starting from hydrogen to zinc pathiyana. There are only two elements which have got abnormal electronic configuration. Okay, that is, yeah, chromium and copper. Chromium with atomic number 24 and copper with atomic number 29. So when you write the usual electronic configuration, it would look like 1s2, 2s2, 2p6, 3s2, 3p6, then 3d0, of course, but 4s2, and then 3d4. But what will happen is 3d4 seems to be partially filled. So can we have a better arrangement is the question. So yeah, 1, 2, 3, 4. So it becomes partially filled. So we modify the configuration and we write it as 3d5 and 4s1. That way, the number of exchanges possible between the 5 electrons in 3D would increase. That would cause it to be stable. So chromium's henceforth configuration will be written as 3d5 and 4s1. Are we clear? Okay. Similarly, for copper, we will say that it is 3d10, 3d9 and 4s2 as per our way of filling up of the electronic configuration. But 3d9 again seems to be partially filled. 1, 2, 3, 4, 5, 6, 7, 8, and 9. But then what will happen here is the 4s is completely filled. No exchanges in this. So one electron will shift into the 3d9 and that makes it completely filled. That allows more number of exchanges as well as a greater symmetry. So this leads to greater symmetry and hence we will put it as the 3d10 and 4s1 as the usual configuration. So sometimes they may ask you what is the abnormal, explain the abnormal electronic configuration. Then you quote it must have been 3d9 4s2, which is modified later as 3d10 and 4s1. Okay. Now, supposing we take carbon. Carbon has got 1s2, 2s2, and 2p2. There are 6 electrons. Okay. The atomic number of carbon is 6 and mass number is 12. So 6 electrons distributed as 1s2, 2s2, 2p2. So it looks like the 2p also seems to be having 2 unpaired electrons. And it would be better if you can shift 1 electron from here to here. Na? But carbon அப்படி நடக்கிறது இல்லை. ஏன் நடக்கிறது இல்லைன்னா progressively we will go and see that suppose எங்கெல்லாம் வந்து energy difference. இப்போ வந்து we are asking the electron from the fourth shell to get inside the third shell. Correct? Whereas here, it is between the same principal quantum number. Okay. Idea is when we look at the first shell, நம்ம Bohr's model பண்ணும்போது, we will actually calculate the energy difference between the various shells. What we will see is the energy difference between first and the second is maximum difference. And progressively it keeps reducing. So by the time I come to 1, 2, 3, and 4, the energy difference here is quite small. That allows an electron from the 4s to get inside the 3d. Also, it is getting nearer to the nucleus, correct? It is going from 4s to 3d. It is getting nearer to the nucleus, number one. So the energy difference is also quite small. So that allows the electron of 4s to move into the 3d. But an electron present in s is very, very penetrated. We will talk about something called as penetration effect. Okay. That is, an electron present in S is most closest to the nucleus than P, than D, than F. So this goes like that. So Why to have electron move from an orbital which is very much attracted by the nucleus into an orbital which is not so attracted? Understood? The electron in S is the most. எப்பவுமே பாத்தீங்கன்னா, whenever we look at any particular shell, it is the S which is getting the electron first, then only P, then only D, then only F. Why? Because the energy present with an electron when it is in S is very less and it is very well attracted by the nucleus. So both the electrons are well attracted by the nucleus. So why would it go to, sorry, is it எதுக்கு S க்கா? Filling up of the various orbitals happens in increasing order of energy. So which has got lesser energy, 2s or 2p? Apo electron would rather like to stay in 2s than in 2p. Whereas here it was moving from the fourth to the third shell. Na? Understood? So it is coming closer to the nucleus. Yeah, yeah. Okay, so that's what I said. From 1 to 30, from the 1 to 30 elements, the abnormal electronic configuration concept is exhibited only by chromium and copper. You cannot take carbon as anything exceptional going inside it. Okay. So there is no shift, and this is the usual electronic configuration. Do not try to make the P half filled. Don't try to shift the electron. Okay, there may be a cross question. You will not normally do, but there may be a cross question. So in that case, you can, yeah, exception. You can't say that the electron is moving to create a half field. You don't do that, I'm saying. You don't shift an S here. And the reasons will be number one, the energy difference between the subshells S and P is quite larger compared to 4s and 3d. And number two, if an electron is more number of electrons present in the 2s is more stable than electron present in 2p. So stability wise also it is beneficial. Okay. Yeah, I will put it as number one, the electrons in 2s have lower energy than being in 2p. So the electrons do not move from 2p, sorry, 2s to 2p to cause or to form half-filled configuration. Okay. So they do not, okay, they do not shift. Number two, the energy difference is too large to cause a shift of electron from 2s to, okay. So that actually completes our electronic configuration, right? Okay. If you want to look at how the various orbitals are அப்படின்னா, supposing I'm talking about, say, an element like neon, which has got 1s2, 2s2, 2p6 configuration. Then S would be spherical in nature. 2s will be spherical in nature, but larger. Then 2p will be 2px, 2py, and 2pz, and each one of the orbital contains two electrons. So I'll put just two dots. Okay. Two dots. Fine. Okay. But how are they actually arranged? If the neon's nucleus is this with 10 protons, the 1s, I'll put it with a different color. 1s would be somewhere like this. It's spherical, not a circle. Okay. It's spherical. 1s is this. Let us assume that the 2s is this. Okay. Then where is the 2p? The 2p will be somewhere like this. 2p will be an orbital originating from the center. This is 2py, 2px, and 2pz. Is it okay? So supposing we have some more like 3s, 3p6, and 3d something, then 3s would be still larger one. Assume that this is your 3s. Okay, 3p. Okay. And similarly, 3D. 3D no complicated item, correct? Okay. So இதுதான் வந்து I was actually trying to show you. I don't know whether I showed you with this. There is an Z period app அப்படின்ட்டு ஒன்று இருக்கு. Wherein, if you look at, see, இது என்னன்னா basically how this platform will help in some ways, okay, not always, will be, say, for example, I want to look at the first, say, melting point, okay. In the entire periodic table, remember, in the earlier classes, you were told that tungsten is used as the material used for making filaments. Mm. Mm. Because it has got the highest melting point, right? Carbon is also high. Why? Carbon is diamond. One of the allotropic forms of carbon is diamond, which is having quite high melting point. So if you see, this is the range of color. The lower ones will be shown with the light blue. Changing color, that means changing melting point. So then fluorescent green, then yellowish, then orange, and then finally dark red. So the highest ones will be represented with a dark red. So if I keep moving, see, if I scroll, the ones which have been, this is melting point. That means temperature at which the solid is converted to the liquid. So those which are already converted will be not highlighted. That means they have already melted. They have already melted. These are all melting at this temperature. So watch for iron. Watch for iron. Iron is still solid. Iron is still solid. And now see, somewhere here, right? Around this temperature. See, around 1498 roughly. You can't exactly say, at around that temperature. So அப்படியே போனீங்கன்னா, see, all these are melting. Carbon is also gone. See, carbon வந்து highlight பண்ணல because there are allotropic forms. So right now you have got the tungsten alone. See, highest temperature, tungsten alone stays. And when we further increase the temperature, even that melts. இந்த மாதிரி நிறைய ப்ராப்பர்ட்டிஸ் இருக்கு. Okay. Okay. Anyway, electronegativity is one another very important category to see. Okay. நம்ம இதை பார்ப்போம். We'll see when we come to periodicity of elements. அப்போ நம்ம பார்ப்போம். So nitrogen is quite high. See, nitrogen is quite high. Nitrogen, oxygen, fluorine, chlorine, bromine, etc. are quite high. Okay, what I wanted you to see now is this. The electron, this is your D subshell. One of the subshell is given. Okay. Now, so dz square is an orbital located on the z axis, and there is a disk present on the xy plane. Remember? We had this. So dz square, d orbitals picture நம்ம பார்த்தோமா? No, na? Did we see? D, yeah, this one. So இந்த மாதிரி z axisல வந்து there is a low. This is on the z axis. There is a low, and there is a disk on the xy plane. Okay, this one. So இதோட picture தான் அங்க இப்போ காமிக்கிறேன். This is that. Understood? On the z axis there is a low, and on xy plane there is a disk. இது வந்து one of the f orbitals. So it's very complicated to draw. இப்போ இது என்னன்னா, say K shell. So I'm going to not highlight. So K shell there will be only S, which looks spherical. Okay, இப்போ L பார்த்தீங்கன்னா என்னென்ன ஹைலைட் ஆயிடும்? SO இருக்கும், PX, PY, PZ. So இப்ப பாரு. This is what. So ரொம்ப blurred-ஆ கொடுத்திருப்பாங்க. So this is first, this is the S. உள்ள ஒரு sphere தெரியும். That is your 2S. Then you see some dumbbell shaped regions. That is your PX, PY, etc. இப்படி overlap ஆகும். What I am trying to say is, இப்போ M shell வந்துச்சுன்னா 3S, SPD மூணுமே இருக்கும். So even more. So they are all overlapping regions. அப்போ 1s இருக்கிற இடத்துல 2s இருக்காது. 2s இருக்கிற இடத்துல 3s இருக்காது இல்லையா? 1s இருக்கிற ரீஜன்ல 2s எலக்ட்ரான் இருக்காது. 2s இருக்கிற ரீஜன்ல 3s இருக்காது. 3s இருக்கிற ரீஜன்ல 4s இருக்காது. அதே மாதிரி 2p இருக்கிற எலக்ட்ரான்ஸ் ரீஜன்ல 3p இருக்காது. And so on. Okay. So இந்த மாதிரி கொஞ்சம் காம்ப்ளிகேட்டடா தெரியும். Okay. I'm just trying to move it. Okay. No. This எல்லாம் you will not be. மேக்ஸிமம் என்ன கேட்பாங்கன்னா d ஆர்பிட்டால்ஸோட மேக்ஸிமம் S, P and D அவ்வளவுதான். இதோட ஷேப்ஸ் மட்டும் தான் கேட்பாங்க. ஓகே, அது கூட ஈஸியா போட்டுடலாம். We can put X. You put X, Y and put the lobes in between. அதே மாதிரி இப்போ Y, Z அப்படின்னா இப்படியே வரை Y and Z. So you are turning the plane for you to draw it easily on the plane of the paper. This is ZX. X is Z axis. So நம்ம திருப்பி வரைஞ்சுக்கிறோம். லேபிள் பண்றது தான் வெரி இம்பார்ட்டன்ட். dx square first 3 பட் டிஃப்ரெண்ட் பிளேன்ஸ்ல இருக்கு. இது வந்து XY பிளேன்ல இருக்கு, இது YZ பிளேன்ல இருக்கும், இது ZX பிளேன்ல. ஒரே மாதிரி. ஏன்னா நான் திருப்பிக்கிறேன். ஏன்னா இந்த மாதிரி வரையறது எவ்வளவு பேர்னால முடியும்? அதனால we are labeling the axis YZ and label பண்ணிட்டோம், which is lying flat on the paper. அதே மாதிரி XZ. Normally நம்ம the Y தானே சொல்லுவோம். We are turning and drawing it on the paper. This is X square, Y square, dx square, Y square. So both the lobes are on the axis line, on the X and Y axis line. Okay. This is Z square, which is one lobe on the Z and one disc on the XY plane. So this is Z axis. So dz square. Okay. At the most, இவ்வளவுதான் draw பண்ண கேட்பாங்க. சரியா? Okay. இப்போ உங்க ஸ்கூல்ல is there any platform where you have got previous year questions loaded or anything anywhere? Nothing. No. What's the name of your school? Okay. முடிஞ்சா எனக்கு அந்த குரூப்லயே உன்னோட ஸ்கூல் பேரை போட்டு. Okay. Then why is ZX DXY மூணு ஆக்சிஸ்லயே மாறி மாறி என்னென்ன இருக்கு? XY Z. So XY YZ அப்புறம் XZ. Okay. So DXY போடும்போது நம்ம என்ன பண்ணுவோம்? This is XY plane இல்லையா? XY plane எப்படி இருக்கும்? This is X axis, Y axis. So the plane will be this plane, right? அதுல ஆக்சிஸ்க்கு நடுவுல ஆர்பிட்டால்ஸ் இருக்கு. This is XY. இப்போ DYZ அப்படின்னா Y is this and Z is this. அப்ப நம்ம பிளேன் எந்த பிளேனை பத்தி பேசுறோம்? இந்த பிளேனை பத்தி பேசிட்டு இருக்கோம், ரைட்? அதுக்கு நடுவுல. சோ இது எல்லாருக்கும் வரையறது கஷ்டம். அதனால என்ன பண்ணுவாங்கன்னா this is Y, this is Z ன்னு சொல்லி அந்த ஆக்சிஸை டர்ன் பண்ணி டயக்ராம்ல காமிக்கிறோம். வேற ஒன்றும் இது அப்படியே we are making it to lie flat on the paper and show. Is it okay? So மூணாவது என்ன இருக்கும்? DZX. So Z axis இது, X axis இங்க இருக்கு. So அந்த பிளேன்ல உனக்கு லோப்ஸ் இருக்கும். Okay. But again, it's very difficult for some, not for all. So we'll put it as this is X axis, this is Z axis, and we'll put it like this. As long as you're labeling the axis lines, it is okay. Fine. Oh, right. We have completed the electronic configuration. When we look at any of the electronic configuration, we would know the meaning of it, right? what is the meaning, where is the electron going, etc., etc. And we can keep writing for any higher element also. Okay. For example, if I have, say, I think this has to develop even more. Say, number francium edtha kudo, we will be able to write the electronic configuration. Okay. Or any of the element in edtha kudo, we will be able to write the electronic configuration. Okay. So that way, see, look at this. So when you click on it, there is some information. Okay. Even there is some information about this. Now, this is the way the electrons are. But do you think they are all நம்ம usual solar system le காமிப்போம்ல? Do you think all the electrons will be in one single plane? No, no need at all. It's spherical. Even the S subshell is spherical. அப்ப ஸ்பியர்ல எங்க வேணாலும் இருக்கலாம். அப்போ it's not right to show everything on the single plane. Okay. So I'm just here to explore. நானும் explore பண்ணணும் இது. ரொம்ப பண்ணல. I like this. At least some of the part. Okay. So we'll go back to our lesson. Okay. So நம்மளோட purpose என்ன சொன்னோம்னா, that we understand the electronic configuration completely. Given the atomic number, you will be able to write the electronic configuration. And we are also aware of the fact that no two electrons in an atom can have same set of quantum number values. Okay. So Pauli's exclusion principle. Okay. So number ஒரு electron oda address நம்மளுக்கு தெரியும் இப்போ. So now we are beginning our lesson. Okay. உங்க ஸ்கூல்ல இது ஃபுல்லா பண்ணியிருக்காங்கன்னு சொல்றீங்க. இல்லையா ஃபர்ஸ்ட்ல இருந்து பண்ணியிருக்காங்க. Okay. So we will try to understand about the discovery of the subatomic particles. The first one. Okay, Dharalama. You prefer, you arrange. Both of you are in the same class, no? So I don't mind. Okay. Okay, photoelectric effect புரிஞ்சிடுச்சா? Okay. Oh, no, you'll have to, okay, understand this. Okay, சரி நான் இங்க இருந்து ஆரம்பிக்கிறேன். We'll see. Bohr's model. இதெல்லாமே over. I mean, it should be over before we come into this. So we will start with this. Evidence for the quantized electronic energy levels. இங்க இருந்து ஆரம்பிக்கலாம். Okay. So we'll see 3:16 ஆகுது. Another half an hour I have. Let us see how much I can finish. Okay. So basically Bohr's model. Okay. How it is different from the Rutherford's model in Patina. In Rutherford's model was based upon one experimental detail. He bombarded the gold foil with alpha particles. Okay, alpha particles. And what he found was most of the alpha particles could penetrate through the gold foil. Okay, some of the alpha particles rebounded, very few. Say 1 out of 12,000, 20,000 were rebounding back, and some of them got deflected. So in order to track what is the behavior of the alpha particle, he placed a circular sensitive disk. Okay, zinc sulfide disk to find out where the electrons are, where the alpha particles are moving and hitting. So based on the information, most of the alpha particles could travel straight. So based on this information, he predicted that alpha particles are di-positive helium. Alpha particles are equivalent to di-positive helium atoms. Okay. So being positively charged and the fact that very, very few alpha particles are rebounding, he defined that the nucleus that is the atom should have a very small region inside with positive charge in it. Okay. Because very few particles are actually coming back. So when there is a shower of alpha particles, only a few will go and directly hit it. Na? The ones which directly hit will get rebounded back. So the one which directly hit it will get rebounded. So counting the number of how many particles rebounded back, he predicted that the size of the nucleus is very, very small and it has got the positive charge in it. Okay, most of the alpha particles could travel straight and those which were moving very close got deflected. So the number of deflections were also less. So that also gave the evidence that the nucleus is very small. Okay. Most of the region around the nucleus is empty and the electrons are present in that. Okay. Okay. Now, now the Rutherford's model says that the electrons are continuously moving. Now, electron is having a negative charge. So, when a charged particle moves in a circular orbit, in order to keep its path, keep its circular motion, it needs to continuously accelerate. And if it has to accelerate, then it will keep losing its energy. When it keeps losing its energy, it will come closer and closer to the nucleus. And at one point of time, it will go and hit the nucleus. So that would make the atom unstable, right? Okay. Bohr's model என்ன சொல்றாங்கன்னா, the first, the heading itself, the quantized energy levels. Bohr says the same thing. The atom has got a small positively charged nucleus. The electrons revolve in a particular allowed orbitals. Only certain allowed shells energy levels are possible where the electrons can be present. And as long as the electron is orbiting in that energy level, the electron is not losing energy. இங்கதான் the difference between Rutherford's model. Rutherford model did not define the energy of an electron. So according to other people, when electron is going to be negatively charged, and conceptually they know that conceptually, okay, that they know that being a charged particle, when it has to maintain a circular orbit, it has to keep accelerating. To accelerate, it will spend energy. By spending energy, one fine day, it will come and hit the nucleus. So the atom is going to be unstable. But when Bohr proposed his model, he said nothing like that. And the electrons are present in various energy levels. And as long as the electron is not given extra energy, it will continue to remain in that energy level. That means there is no chance of electron coming and hitting the nucleus. Got it? இததான் வந்து quantized energy levels அப்படின்றோம். Evidence for the quantized electronic energy levels. So quantized certain amount of, இப்போ சே இங்க இருக்க இந்த நம்ம எலக்ட்ரான் பத்தி பேசினோம்ல, அப்போ இங்க இருக்கும்போது ஒரு எனர்ஜி, இங்க இருக்கும்போது ஒரு எனர்ஜி, அப்படியே குறைஞ்சினே வருது பாரு, குறைஞ்சினே அப்போ all these values are possible for the electron ஆயிடுச்சு இல்லையா? ஆனா Bohr says nothing like that. Only see, when you enter into the class school, okay, you would have gone through what, LKG, then UKG, then you would have gone to first standard, second standard, and you have come to 11th standard now, correct? Were you ever in 2.5 class? No, you were in 2 or in third class. You are in 11th or in 12th. So he defines like that, like the various classes are defined for a student. The various energy levels get defined. So Bohr says that electron can be present either in the first shell with some X amount of energy. If not, it will be present in the next level with Y amount of energy. If not, it will be present with, say, Z amount of energy. If not, it can be present with P amount. This is quantized energy level. The quantity of energy possessed by an electron is defined, and it seems to be stationary energy state. That means its electron is not stationary. Stationary energy. Energy is stationary. That means there is no change in the energy as long as the electron is revolving around the nucleus in that particular orbit. So that means there is no chance of electron continuously losing energy and coming and hitting the nucleus is not a chance, Leah. This is the meaning of the quantized energy level. So Bohr defined certain energy levels. He said that only certain allowed energy levels are possible within an atom. Electrons will be present in those fixed energy levels. As long as they are present in that energy level, they do not lose their energy. There is, and if they want to move somewhere, where they will move, they will be what is the difference between what is the energy of the electron in the first shell, X, in the second shell, Y. So supposing I'm giving Y minus X amount of energy, electron will accept it, and electron will jump from the first into the second. If it wants to go to the third, it will take the energy equal to Z minus Y. It will go there. If it wants to go to Okay, assume that y minus x is say 100 units. Now I have only 80 units to give. What will electron do? To go from the first shell to second shell, a minimum of how much energy is required? But I am giving it 80. Electron rejects. It won't move. Yes. Understood? Understood? Similarly, if I am giving Z minus X, then it will go from the first to straight away the third. If I am giving P minus X amount of energy, it will go from the first to the fourth, and so on. Or from second to the third, or from third to the fourth, or second to the seventh, or from fifth to the seventh, and so on. But there is no possibility of electron absorbing energy less than these values. Apo, we are able to define, if a possibility, electron can absorb y minus x, or it can absorb z minus x, or it can absorb p minus x, at least number diagrams, or it can absorb z minus y, or it can absorb p minus y. Any other possibility? Z minus x எழுதிட்டோமா? Yeah, y minus x, z minus x. Okay. இங்க வந்து z minus y and p minus y over. Okay, p minus z is also there. இப்பத்துக்கு these are the possible. அப்போ he is defining that an electron can take this much energy or this much energy, or so not all energies are allowed for an electron. That means an electron cannot be, இப்ப இங்க இருந்தா y amount of energy, இங்க இருந்தா x. Can it have anything in between? So that is why we say quantized energy levels. So the energy with a particular energy with a particular level is fixed, and that is what is said to be quantized. Quantized. Quantum means quantity. So it is quantized. இவ்வளவுதான் இருக்கணும். Understood? Okay. He is defining the energy of each level. Okay. Okay. Where the electrons can be present. But now, how did he come to this conclusion? Okay. How did he come to this conclusion? So, what basically he did was he did spectral analysis. He did spectrum. Okay. Basically, spectral analysis. Pannar. Okay. He actually got the information from the spectral analysis. Okay, what is that spectral analysis? See, what happened was that Bohr's proposal was more or less based on the spectral analysis. So, what people did was they took hydrogen atoms because it contains just one proton and one electron. So, it's the simplest of all. Hydrogen atom will have just attractive force between proton and electron. If say helium எடுத்துக்கணும்னா, it is having 2 and 4 atomic number. So it will have 2 electrons, 2 protons. Then electron will attract the proton 1, proton 2. Proton will attract the electron 1, electron 2. Electron repulsion, proton repulsion. So நிறைய forces ஆயிடுச்சு, correct? So understanding this picture is very difficult. This is electron, proton. This will attract this and this. This will attract this and this. Okay. And these two will repel. These two will repel. So minimum of 1, 2, 3, 4, 5, 6 forces study பண்றத விட hydrogen is simplest. Only attractive forces between one proton and one electron. So he took the hydrogen atoms. Okay, in atomized form, and exposed them to electromagnetic radiations, which happens to be continuous. So you have to understand what is meant by continuous spectrum, continuous form of electromagnetic radiations. What is meant by continuous spectrum? See, when you look at electromagnetic radiation, this is how the electromagnetic radiation propagates. Okay, from one point to the other. What are electromagnetic radiation? The light which we see now, which we are receiving, is also electromagnetic radiations. The light emitted by the bulb in your home, the light coming from the sun to us, all these are electromagnetic radiation. The light is basically a form of energy which travels as electromagnetic radiations. Okay. So this electromagnetic எதுக்கு சொல்றோம்னா, it has this is the path of propagation. அப்போ this is the electrical component of that radiation and the perpendicular plane magnetic part of that magnetic component of that electromagnetic radiation is there. Okay. So it travels in the form of a wave. Okay. When it is traveling in the form of a wave, it should have certain frequency, certain wavelength. Okay. Ipo, when all the electromagnetic radiations are arranged in decreasing frequency or increasing wavelength, what we are getting is an arrangement, okay, of the radiations, which is continuous. What is meant by continuous? Continuous, na, there is no gap. That means, நான் என்ன பண்றேன்னா போயிட்டு see this is the electromagnetic spectrum, the spread of whatever possible electromagnetic radiations are there. Okay, அதுல ஒரு small part of it is actually visible to our eyes. Rest of it is not visible. We can't see ultraviolet, X-rays, gamma rays, infrared, microwaves, etc. We can't see. Okay. Now, இது ஒரு பெர்ஸ்பெக்டிவ்க்கு தான் கொடுத்துருக்காங்க. What we see around is a small part of the electromagnetic spectrum. இப்போ நான் என்ன பண்றேன்னா, I am going to go for, say, 400 nanometer na, it is violet in color. 500 nanometer na, it is, or somewhere here, it is perfectly green. Correct? This is around 700, it is perfectly red. But what I'm saying is, they are all, if you go and choose a particular wavelength value, correspondingly, there will be one electromagnetic radiation present. That means it is continuous, no gap at all. Supposing in your class 40 students are there, you people are writing the test out of say 100 marks. Some would have got 10 marks, others would have got 12, then 25, then 45, then 70, then 80, 90. Can you assure me that every possible marks will be there? Is there anybody who is scoring 5 marks in the class? No, because the highest in the class was how much? The lowest in the class was how much? Apo 500, it's nobody's score. After 10, the next highest score is 12. Apo there is a gap. Nobody has scored 11. So it is a discontinuous spectrum, discontinuous array of marks, correct? Whereas the electromagnetic radiations are continuous. Are we clear? Okay, now coming back. This electromagnetic radiation is given to the hydrogen atoms. Okay, and the response is seen. அப்போ response பார்க்கும்போது there was emission, there was some part of the electromagnetic radiation which came out immediately. What came out immediately was arranged. Okay, so நம்ம பண்ணதும் ஒரு spectrum தான். The spread, we gave the complete spread, or we completely spread, SPR, okay, and we gave a complete spectrum in சொல்லலாம். That is all the complete array in solar. We fed hydrogen atoms with continuous electromagnetic radiation. All possible wavelength frequency values were given. வெளியில வரது பார்த்தா one part came out. Okay. When we arranged, we found that there were gaps. There were gaps. That means இங்க electromagnetic radiations corresponding to these frequency values are there. No electromagnetic radiation corresponding to this frequency. There was something, there is a big gap. So what was obtained was now discontinuous, or the technical term is said to be discrete. What's discrete? Discontinuous means discrete. And discrete and a line spectrum and kuda sollala. Lines will be split, yeah. One, this is one, this is one, this is one. So we get line spectrum abdin solro. Okay. So yeah, all the three are same. Fine. So when a continuous electromagnetic spectrum was fed into hydrogen atoms, a part of those electromagnetic radiations were immediately sent out because they were unused. We'll put it at, you will not find these words in the text, but you will find this word, unused. Okay. Or it was, huh? Yeah. When continuous electromagnetic spectrum was given to hydrogen atoms, some of the electromagnetic radiations came out immediately. I will use the term unused, or technically, this was absorption, contrary to the term absorption spectrum. Absorption spectrum. Absorption அப்படின்றது actually இங்க unused. Absorb ஆகாத spectrum. Yeah. Yeah, இல்ல. It had it had some collection இல்ல. அந்த collection arrange பண்ணி பார்த்தோம்னா, there are some values, some of the electromagnetic radiations of some frequency values present in it, and the next immediate value was missing. The next was present. The next was present. Then there was nothing in corresponding to those values. So it is no longer continuous ன்னு சொல்ல வரேன். It is, yeah, it is discontinuous spectrum. Okay. Unused தான் அதுதான். அதேதான் unused. I'll show you. The diagrammatically ன்னு. Yeah. இப்ப என்ன ஆயிடுச்சுன்னா, see இதுதான். இப்ப பாரு. This is not full picture. See. Can you see that this looks exactly negative of this? அப்போ இது வந்து என்னது? இங்க nobody. Okay. So first analyze this part. So நான் என்ன பண்ணேன்னா, when the hydrogen atoms were irradiated with continuous spectrum, something came out immediately. And when something came out immediately was plotted, was arranged, பார்த்தனா, in the values of frequency, there was no radiation present in this part. In the black lines இருக்கிற இடத்துல எல்லாம் corresponding electromagnetic radiations were missing. The black region, yeah, that is missing. Actually, how it would be continuous, yeah, no gaps at all. So that was given. ஆனா வெளிய வந்தது, immediately வெளிய வந்தது என்னன்னா, when you arrange, you didn't find it continuous like the original. You found that there were some missing electromagnetic radiation. So in the value, the electromagnetic radiation corresponding to this frequency was not to be found. Understood? அதே மாதிரி இங்க ஒரு black line இருக்கா? The electromagnetic spectrum electromagnetic radiation corresponding to that frequency value was missing from the spectrum, was not there. So such a spectrum is not continuous because there were some absentees. புரியுதா? So this is said to be absorption spectrum. But contrary to the name absorption ன்னா ஏதோ absorb ஆன மாதிரி தெரியல. ஆக்சுவலா நம்ம ஃபீல் வரும்ல, அப்சார்ப்ஷன் ஸ்பெக்ட்ரம்னா ஆட்டம்ஸ் அப்சார்ப் பண்ணிக்கச்சு அப்படின்னு சொல்ல, அப்படி கிடையாது. தீஸ் ஆர் ஆக்சுவலி அன்யூஸ்ட். ஓகே, அன்யூஸ்ட். பட் ஆஃப்டர் அ டைம் லேக் சம்திங் எல்ஸ் கேம் அவுட். That was also discontinuous. And it was exactly opposite of absorption spectrum. In the absorption spectrum, the electromagnetic radiations which were missing were found. Understood? So, in the black line, this is a black line, but correspondingly, there is a yellow color. So, it's absent from here, but it is present here. Are we clear? Okay. So, what came after the absorption spectrum is said to be emission spectrum. So, the two terms should be understood. So, I use the word unused electromagnetic radiations for absorption spectrum. I will say that these were used by the atoms. The emission spectrum. Illa dear, if I say for example, என்கிட்ட வந்து ஒண்ணுமே இல்ல. See, understand this way. இப்ப நான் ஒரு நம்பர்ஸ் எழுதுறேன். 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. சரியா? And I am giving it to Yalini. Okay, Yalini, HINI. Okay, okay. இப்ப யாழினி என்ன பண்றான்னா, I want you to choose the numbers which you like. Okay. So you are choosing and you are rejecting some. You are rejecting some. Okay. You are choosing some, picking some. என்னென்ன pick பண்ணுவ சொல்லு? 7, 8, வேற 10. You picked. Okay. Maybe உனக்கு 3யும் கொடுத்துறேன் நான். Okay. Okay. அப்போ இத நான் பிளாக் டயக்ராமா வரையறேன்னு வச்சுக்கோ. இதையும் நான் பிளாக் டயக்ராமா வரைஞ்சா நான் என்னென்ன நம்பர் எழுதுவேன்? 3 எழுதுவேன், 7, 8 and 10. அப்போ மீதி எல்லாம் இங்க இந்த வேல்யூக்கு you did not choose, no? You did not choose the number corresponding to this value, na? You did not choose 1, you did not choose 2, you did not choose 4, you did not choose 5, and you did not choose 6, etc. Right? So they will be absent from this picture, na? Where they will be present? So what will be present here? 1, 2, 4, 5, 6, 7 and 8 will be not there. Here it will be absent. Then 9 will be there, correct? What is absent here will be present here. Still, both of them are arrangements. This is continuous, but these two are discontinuous, na? Understood? So, எங்க இல்லையோ நாங்க dark color போட்டுறோம், black color போட்டுறோம். Try to understand. Understood? I'm going to draw the black. I'll tell you. First thing, use na எதுக்காக use ஆகுதுன்னு சொல்லணும் இல்லையா? So, these 7 and 8 are missing. Okay? இப்போ இங்க என்னன்னா 1 and 2 இருக்கிற regionல dark-ஆ தெரியும். இங்க dark-னா அங்க bright-ஆ இருக்கும். இங்க dark-னா that means it is missing from here, but it is present in this part. Got it? Okay. இப்போ first, what is used, what is unused? அப்படின்னா என்னன்னா, whenever you are giving the electromagnetic radiations to atoms என்ன பண்ணோம்னா, say I'm going to make you stand here, Yalini, and or Yalini and few more people like Yalini, okay? Few more replicas of Yalini, and I'm going to throw balls. One ball is of this size, one is of this size, one is of this size, slightly bigger. Okay, I'm going to throw a number of balls. Fine. Okay, some are as big as this. I'm going to throw all these balls to you. To Yalinis, okay? Like hydrogen atoms. So what Yalini can pick, no. Yalini can catch this ball. Can catch this ball, can she? It's too big for her. Isn't it too big? Okay, can she catch this ball? It's very small, tiny. There are microscopic balls also. There are all sizes of balls. So she will pick a few. Too small, she will reject. Too big, she will reject. She may pick a few, right? So what she picked comprises of emission spectrum or the used ones. And what she could not pick is not suitable for her. What is not suitable for you? The microscopic ones you can't catch. The bigger ones you can't catch. So they are unused. That forms the absorption. Unused. Understood? So when electromagnetic radiations are given to atoms of hydrogen, hydrogen finds some of them suitable for itself and others not suitable for it. The others which are not suitable for it are immediately given out, and that forms the absorption spectrum. So whichever is absent from this picture is probably the ones which Yalini took it, na? So what hydrogen took is now arranged separately, and that is said to be the emission spectrum. Understood this picture? அதனால தான் emission spectrum and absorption spectrum look opposite of one another. They look negatives of one another. Emission spectrumல இருக்கிறது absorption spectrumல இருக்காது. Absorption spectrumல இருக்கிறது emission spectrumல இருக்காது. Got it? Okay. இப்போ ஹைட்ரோஜனுக்கு எது வேணும் எது வேண்டாம்? Emission spectrum வேண்டாம் எமிஷன் வேணும். இப்போ இந்த இந்த ஹைட்ரஜன் liked the emission spectrum part, that is some of the frequency values it liked, correct? And it took, right? Does it not, what it took, does it not tell about hydrogen? It does it not tell about the makeup of hydrogen atom? Either which we can understand the hydrogen atom. For example, I am sending you into a buffet. Yalini, I am sending you into a room where a number of plates containing different kinds of dishes are placed. And I have a count. Each plate has got what? How many pieces of each kind? And I am not inside the room. Okay. And after you have had your food, you are coming out. Then I go inside and check. Will I not be able to know what is your choice, Yalini? போய் அந்த பிளேட்ஸ பார்த்தாவே தெரிஞ்சிடும். இந்த பிளேட்ல there were 10 pieces of gulab jamuns. Now only 8 are left behind. So Yalini likes 2 gulab jamuns. Okay, Yalini does not like pineapples because I placed 10 pineapple pieces. All the 10 are intact. அதே மாதிரி இப்போ what hydrogen took, what hydrogen used will describe the structure of hydrogen atom. Understood? Okay. இப்போ என்ன பண்ணாங்கன்னா, come to this part. இப்போ emission absorption spectrum completely understood. Okay. இப்போ என்ன பண்ணாங்கன்னா, various scientists, no, they were finding this emission spectrum and absorption spectrum very curious. They were very interested in why only these are used up, why these are coming out so fast, why this is coming out late, and why this is used and that is unused. Abdine, many scientists started probing. Okay, so what is this again? These are arrangements of electromagnetic radiations in decreasing order of frequency and increasing order of wavelength. இல்லையா, நம்ம எப்படி அரேஞ்ச் பண்ண போறோம்? அது be it absorption or emission spectrum, frequency values வச்சு அரேஞ்ச் பண்ணும், இல்ல wavelength values வச்சு அரேஞ்ச் பண்ணியிருப்போம். ரைட்டா? Right. So various scientists were curious about why these are appearing now. அப்படின்னு each scientist wanted to study. Okay, it would look too complicated. So people started studying each patch. They started studying it in patches. ஒரு small part எடுத்து இந்த வேல்யூ ஏன் வருது, இந்த வேல்யூ ஏன் வருது, இந்த ரேடியேஷன் having this value of frequency ஏன் இங்க வருது, ஏன் இந்த why did the atom needed that அப்படின்ட்டு they started probing. So what they said was the mathematical expression, which was the mathematical expression given for the radiations of these values were now mathematically presented, and Balmer gave one equation which is popularly called as Balmer's equation. What did it look like? It said that the wave number is represented with, what is wave number, remember? 1 by lambda. Very good. So the wave number of the radiations belonging to one section of the emission spectrum could be mathematically represented by saying it is 109677 1 by n1 square minus 1, actually 1 by 2 square minus 1 by n square centimeter inverse. What is the meaning of that? I told you, no, that in emission spectrum there are certain presence and certain radiations are absent, correct? This is present, this is present, this is absent. So people were probing the different zones where the electromagnetic radiations of certain frequency values were found. In the electromagnetic radiations of these frequency, nu 1 frequency irukku, nu 2 irukku, nu 3 irukku, அப்படின்னா lambda தெரியும். Frequency na lambda தெரிஞ்சிடுச்சு. இல்லையா? We know how they are related. C is equal to mu lambda. So frequency தெரியும்னா அதோட lambda calculate பண்ணிக்கலாம். Okay. அப்ப இந்த lambda இருக்கு, மத்த இந்த lambda values காணோம், right? எதெல்லாம் இருக்கோ they comply with this equation. So any electromagnetic radiation which corresponds to, when I substitute n value greater than 2 in the particular equation, if I substitute This is 109677 1 by 2 square minus 1 by n square, where n is greater than 2. This was the suggestion by Balmer. Okay, இப்போ நான் என்ன பண்றேன்னா, when I substitute 3, I'll be getting one wave number, invert it, I get some lambda value. Na? This particular electromagnetic radiation with this wavelength value is found in this region. So he enumerated a formula. So if you substitute n is equal to 3, okay, or n is equal to 4, or 5, or 6, what is n? N should be greater than 2. So n should be greater than 2 means n can be 3, 4, 5, 6, 7, etc. When you substitute the value and get the lambda, that particular lambda corresponding electromagnetic radiation is present in the line spectrum, the emission spectrum of hydrogen atom. So lambda 1 is there. If I 4 substitute பண்றேன்னா எனக்கு lambda 2 கிடைக்கும். Is it there? Yes, it was there. When I substitute 5, I get a lambda, that is lambda 3. Is it there? Yes, it is there. When I substitute 6, I'm getting lambda 5. Is it there? Yes, it is there. When I substitute 3.5, I still get a lambda value. Na? நான் இங்க n-க்கு பதிலா 3.5 substitute பண்றேன். n-க்கு பதிலா என்ன பண்றேன்? 3.5 substitute பண்றேன். அப்பவும் எனக்கு ஒரு lambda value கிடைக்கும். அது பார்த்தா இந்த எமிஷன் ஸ்பெக்ட்ரம்ல இருந்து காணும். எங்க இருந்தது அது? எங்க இருந்தது? எமிஷன்ல இல்லனா எங்க இருக்கும்? Absorption. அப்போ the hydrogen atoms needed these electromagnetic radiations and did not use these. Understood? Understood? Okay. இப்போ இதை எப்படி யூஸ் பண்ணாங்க? இப்போ we know 1 by lambda is equal to 109677 1 by n1 square minus 1 by n2 square அப்படின்ட்டு because I told you the picture was too complicated and many scientists were working, but they were analyzing different patches of electromagnetic radiation, the emission spectrum. One was studying, say, this patch, second was studying this patch, another one was studying this patch, and so on. Balmer's equation was this equation. But when other scientists found out, when the other scientists were analyzing the rest of the parts of emission spectrum, they could generalize this expression and they could say, no, it is n1 square minus n2 square. So if the wave, the electromagnetic radiation of this particular lambda is found here, which happens to, okay, which will be when n1 is equal to 4 and n2 is equal to 6. Something like that. Okay, so they generalize the formula. Balmer could say that it is 2 square to n square, but others could generalize. No, it's not just for this patch. The equation what you have invented is for the entire emission spectrum, and let us generalize it and put it as n1 square and n2 square, where n1 is always less than n2 if it is this equation. Fine. Okay. இப்போ என்னன்னா, I'll tell you. இப்போ இதோட என்னன்னா, see, we know E is equal to H nu, and we know E is equal to Hc by lambda. Okay, அப்போ நான் இங்க Hc ரெண்டு பக்கமும் மல்டிப்ளை பண்ணிட்டா எனக்கு இது எனர்ஜி கிடைக்காதா? ஓகே, இப்போ நான் இந்த ஈக்குவேஷனை எனர்ஜி ஈக்குவேஷனா எழுதிக்கலாம். டெல் இன்னு ஏன் போடுறேன்னு சொல்றேன் நான். ஸோ ஹெச்சி இதோட மல்டிப்ளை பண்ணிட்டா நம்மளுக்கு என்ன வருதுன்னா 2.18 into 10 to the power minus 18 வரும். ஓகே, Planck's constant is 6.626 into 10 to the power minus 34. C is 3 into 10 to the power 8. எல்லாத்தையும் மல்டிப்ளை பண்ணா 2.18 into 10 to the power minus 18 1 by n1 square minus 1 by n2 square வந்துடுச்சு. இப்போ என்ன, வாட் இஸ் த டிஸ்கஷன்? என்ன டிஸ்கஷன் அப்படின்னா, இந்த n1 அப்படின்றது ஷெல் நம்பர் 1. this is lower shell And this is any higher shell. Any higher shell. It can be 2, it can be 3. Which one? N1 is any lower shell, not just one, any lower shell. Any lower shell. Okay. So supposing இப்போ நான் வந்து செகண்ட் ஷெல்ன்ற or it could be reverse also. ஏன்னா எலக்ட்ரான் வந்து மேல 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 போயிட்டே இருக்காது. It can come down. So when I said that a part of electromagnetic radiations were used by the atom, அப்போ usedனா என்னாச்சு? Actually, an electron in present in the hydrogenல basically electron first shellல தான் இருக்கும் இல்லையா? So first shellல இருந்து கொஞ்சம் எனர்ஜி எடுத்து எவ்வளவு எனர்ஜி எடுத்து energy with the first is E1, energy with the second is E2, E3, E4, E5. இப்போ நம்ம E2 minus E1 அப்படின்ற எனர்ஜி கண்டினியூஸ் ஸ்பெக்ட்ரம்ல இருந்து இருக்குமா இருக்காதா? ஏதோ ஒரு ஃப்ரீக்வன்சி வேல்யூ அந்த எனர்ஜிக்கு ஈக்குவலண்டா இருக்கும்ல E2 minus E1 அளவுக்கு எனர்ஜி வச்சிருக்கோம்ல. That particular radiation was used by this electron to move into the second shell. And when you say a box of hydrogen atoms, ஒரு ஹைட்ரோஜன்ல எலக்ட்ரான் E1ல இருந்து E2 போகுது, இன்னொன்னுல E3ல இருந்து E1ல இருந்து E5 கூட போயிருக்கலாம். யூ நெவர் நோ. ஏன்னா இத எல்லா டைப்ஸ் ஆஃப் ரேடியேஷனும் கொடுத்துட்டியே. சோ இந்த ரேடியேஷன்ல E5 minus E1 இருக்கும் இந்த கண்டினியூஸ் ஸ்பெக்ட்ரம்ல. One of the hydrogen atom can take that and excite its electron from the first shell into the fifth shell. Okay. Will the electron always remain there? Is it not high energy state for it? Aufbau's rule. Electrons are filled up in increasing order of various energy levels of the orbits and orbitals. அப்போ fifth shell குள்ள higher energy இல்ல. அப்போ electron அங்கே இருக்காது. அங்கிருந்து என்ன பண்ணும்? It can come down to fourth. It can come down straight from fifth to the third, or straight from fifth to the second, straight from fifth to the one, and so on. அப்போ வெளியே வர்றதுனால எனர்ஜி என்ன பண்ணும்? ரிலீஸ் பண்ணிடும். That is during when it uses, it is taking the energy to excite its electron. But electron will not always stay there. It will have to come out. When it has to come down, it will give out the energy. And that is what came out was only your emission spectrum. Understood? இல்ல நான் சொன்னல அப்சார்ப்ஷன்ன்றது அன்யூஸ்ட். அதுக்கு தேவையே படல. ஏன்னா அங்க என்ன இருந்தது? ஒரு பர்டிகுலர் வேவ் லென்த் வேல்யூ நெவர் கரஸ்பாண்டட் டு E5 minus E3, E5 minus E4, E2 minus E3, E3 minus E1. It never matched with those values. So it was absolutely waste for atom of hydrogen. So it was unused. Leave it. Okay. So what did it do with what did hydrogen do with some of the radiations? It actually consumed them to cause excitation from the existing energy level to higher energy level, caused the excitation of electron. But electron எப்பவுமே போய் அங்கேயே உட்காந்துக்காது. It will have to come down. So when it comes down, அதை எடுத்த எனர்ஜி அப்படியே வெளியே கொடுக்கும். அந்த வெளியே கொடுத்த எனர்ஜி தான் எமிஷன் ஸ்பெக்ட்ரம். Yeah, obviously. Okay. ஓகே. இப்போ சே ஃபார் எக்ஸாம்பிள் நீ வந்து ஒரு ஸ்டேர் கேஸ்ல நீ ஏறணும்னு நினைக்கிற. ஓகே, யூ ஆர் சோ யங். ஸோ யூ மே டேக் அ லீப் டு த ஃபோர்த் லெவல். கரெக்டா? 1 2 3 4. ஓகே. நீ கீழே வரணும்னா உன்னோட சாய்ஸ் இல்ல. நீ வேணா ஜம்ப் பண்ணிக்கோ, இல்லைன்னா இந்த ஸ்டெப்புக்கு ஜம்ப் பண்ணிட்டு அப்புறமா ஜம்ப் பண்ணு, இல்ல இந்த ஸ்டெப்புக்கு ஜம்ப் பண்ணிட்டு அப்புறமா ஜம்ப் பண்ணு, இல்ல இப்படி ஜம்ப் பண்ணிட்டு இப்படி ஜம்ப் பண்ணு. சோ ரிட்டர்னுக்கு ஒரே வழியா இருக்கு. சோ இங்கிருந்து இங்க வரும்போது you would lose some energy, no? இந்த லெவல் that was given out, that was part of emission spectrum. இங்கிருந்து இங்க வரேன்னா that energy was given out, that was also part of emission spectrum. இங்கிருந்து இங்க வரேன்னா that was given out and that was also part of emission spectrum. அதனால நான் என்ன சொன்னேன், உன்னை நான் ரூம்குள்ள விட்டுட்டு போய் அந்த பிளேட்ஸ பார்த்தேன்னா உனக்கு என்ன பிடிக்கும் தெரியும்னு சொன்னேன் இல்லையா? அதே மாதிரி எமிஷன் ஸ்பெக்ட்ரம் பார்த்தா ஹைட்ரோஜனோட மேக்கப் புரிஞ்சுது. வாட் இஸ் த ஸ்ட்ரக்சர் ஆஃப் ஹைட்ரோஜன் அப்படின்னு புரிய ஆரம்பிச்சது பீப்புள். ஹைட்ரோஜனோட லெவல்ஸ் எப்படிதான் இருக்கு. அப்போ ஓ இப்படி இருந்தா தானே, இப்படி எனர்ஜி லெவல் இருந்தா தானே. அப்போ யாழினி ஜம்ப் ஃப்ரம் தேர் டு ஹியர். சோ இங்க இருந்தா அடுத்தபடியா இங்க இருக்கா. அப்போனா யாழினி இந்த பில்டிங்ல எப்படி இருக்கும் ஸ்டெப்ஸ்? இங்க ஒரு ஸ்டெப் இருக்கு, இங்க ஒரு ஸ்டெப் இருக்கு. யாழினி never this was say 1 meter, 2 meters, 3 meters. Of course, stairs will not be that tall. 1 meter, 2 meter, 3 meter, 4 meter. அப்போ 3.5ல யாழினி லேண்டே ஆகல. That means there is no step corresponding to 3.5 meters. That's what I said. Emission spectrum பார்க்க peopleக்கு என்ன புரிய ஆரம்பிச்சதுன்னா, around the hydrogen atom, the electrons are located in various shells which have got some fixed energy. So an electron in hydrogen can take energy, consume energy from the emission, from the continuous spectrum, can allow its electron go to either second shell or to the third or to the fourth or to the fifth or to the 10th. Who knows? But from 10th, when the electron will never be there, it will not remain in the 10th. It's highly unstable for it. When it wants to move from 10th to the ground level, what is the ground level for hydrogen atom? First shell இருக்கணும். 10thல இருந்து எலக்ட்ரான் எப்படி எல்லாம் வர முடியும்? ஸ்ட்ரெயிட்டா ஒரு ஜம்ப். அப்படி இல்லைன்னா 9th வரலாம், அப்படி இல்லைன்னா 8th வரலாம், அப்படி இல்லைன்னா 7th வரலாம். Eventually 7thல இருந்து திருப்பி ஃபர்ஸ்ட்க்கு தான் வரணும். Understood? So every time it takes a leap from 10th to 9th, some energy is lost, and that energy lost comes out and becomes the part of the emission spectrum. No, it's not equal. Just now I was telling you when I was discussing about carbon, the difference in the energy values keeps decreasing. தூர போக 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 energy difference குறைஞ்சினே இருக்கும். No two shells energy difference is same. அப்போனா நம்மளுக்கு 10thல இருந்து 9th வரும்போது ஒரு எலக்ட்ரோமேக்னெட்டிக் ரேடியேஷன் வெளியே வந்திருக்கு. அதோட வேல்யூ λ1. 9thல இருந்து 8th வருதுன்னு வச்சுக்கோயே, அதோட வேல்யூ λ1 இருக்கணும்னு அவசியமே இல்லை. இட் இஸ் டிஃப்ரெண்ட் எனர்ஜி. ஸோ இட் இஸ் 2. அப்போ λ1 வெளியே வருதா? அப்போனா correspondingly energy is equal to hc by lambda. அப்போ the energy difference between these two or some two steps is so much. அப்படின்னு people started understanding the structure of atom. Understood? For every two shells, it is different. Okay, I'll tell you numerically what it is. Okay, I'll take 5 more minutes. It's going much beyond our regular time, but I'll take 2 more minutes. According to Bohr's model, the energy of a particular shell is minus 2.18 into 10 to the power minus 18 z square by n square. Energy of the first shell, therefore, will be minus 2.18 into 10 to the power minus 18. Z is the atomic number of a. So Bohr conducted his experiment only for hydrogen or hydrogen-like atoms. So Z1 ன்னு எடுத்துக்கலாம். Atomic number of hydrogen 1. So first shell இருக்கும்போது இவ்வளோ எனர்ஜி இருக்கும் அதுகிட்ட. ஒரு எலக்ட்ரான் in the first shell will have so much energy. E2 னா எவ்வளவு இருக்கும்? minus 2.18 into 10 to the power minus 80. 1 by 2 square ன்னு சமா? இது ஹைட்ரோஜனுக்கு மட்டும் தான். நான் சொன்ன பாரு, ஹைட்ரோஜன்ல there was only one proton, one electron. இந்த பிக்சரை புரிஞ்சுக்கிறதுக்கே ரொம்ப மண்டை உடைஞ்சது. அப்போ higher atomsக்கு it is not at all applicable. It is applicable. Bohr's model is applicable to hydrogen and hydrogen like. What is hydrogen like? இப்போ ஹீலியம்ல இருந்து ஒரு எலக்ட்ரான் எடுத்துட்டோம். It contains one electron only, no? But still it is complicated picture. ஏன்னா there are two protons. Hydrogen is simplest, one proton, one electron. Compared to that, helium plus is, even though the electrons are same, the protons are not same, na? So the entire discussion of Bohr is about hydrogen or hydrogen-like atoms. So இப்போ energy of the third shell. An electron is there in the third shell. அப்போ what is the energy na 1 by 3 square. இப்போ difference கண்டுபிடிச்சு பாரு. Can E2 minus E1 be same as E3 minus E2? Check. Definitely different ஆயிடும்ல. E4 minus 2.18 into 10 to the power minus 18, 1 by 4 square. அப்போ E4 minus E3 will be least lesser than E3 minus E2 will be lesser than E2 minus E1. ஏன்னா உன்னோட n வேல்யூ டினாமினேட்டர்ல மாற 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 ஸ்கொயர் அதுவும் ஸ்கொயர்ல மாறுது மாற மாற உனக்கு no two energy levels have got same energy difference. Yeah, E2 minus E1 is the law. Ana, okay. Between two consecutive energy levels, E2 minus E1 da. Yes. Okay. But the largest of all எது தெரியுமா? E infinity minus E1. You are sending the electron from the first shell to where? Infinite shell. Where is that actually? In the work da number ionization. When we say sodium lost its electron, lost forever, it went to infinite shell. Hydrogen lost its electron. Na? Where did it go? It moved from the first shell to infinite shell. Understood? Ipo, when energy of each shell is quantized, remember? Energy of each shell, energy of electrons in each shell is quantized. Then between them, when the electron is moving, only certain frequency values will be consumed by the atom. So only certain frequency values were found in the emission spectrum. So in the emission spectrum padika the energy levels in the atoms became clear. And with the help of this only Bohr proposed his theory of the quantized energy levels. What did he say? That around the nucleus there are certain definite energy levels. That is, first level will have E1 amount of energy, which is minus 2.18 into 10 to the power minus 80 z square by n square, 1 square. So energy of an electron, as long as it remains in this shell, is so much. As long as the electron is in the second shell, it will be E2 is equal to minus 2.18 into 10 to the power minus 18, 1 by 2 square. So if you give energy equal to E2 minus E1, electron agrees to jump into that shell. Got it? And only those electromagnetic radiations which have this much amount of energy will be part of the emission spectrum. Rest are useless. So either this energy is useful for it or this energy gap, whatever electromagnetic radiation is able to give energy equal to what jump this is taking. 1 to 2 க்கு தேவைப்படுற energy எந்த electromagnetic radiation கொடுக்குதோ that will be useful for it, and the others will be not useful for it. The ones which are not useful for it will be rejected immediately, and that forms the absorption spectrum. Understood? Okay. I think it's too much for today. So we'll conclude. இத பத்தி மறுபடியும் we will learn and conclude. Okay. We will understand the various postulates of Bohr's atomic theory. Okay. Yeah. Okay. Yes. Yes, bye.